Again, so I'm Jeremy. I'm a database engineer at AWS working with Postgres engines. Now, we just finished a presentation with Vinny that he gave a very good, he actually went a lot deeper too. There was a lot of depth in that. I mean, we have already introduced the general block structure. We've already introduced the general concept of MVCC. This is a relational database. Relational databases, what does that mean? That means a lot of things, but a couple of things that means is for one, like transactions. Another thing is consistency, meaning I can define constraint, or I can sort of define invariants, things that must be true about my database. For example, I could say that I have these two tables, and this record over in this table must always have a corresponding record in that table. We call that a foreign key. I could say that in this table over here, this thing is unique, meaning there's never two records that have identical values. And the database just takes care of that for you then. You don't have to write error handling code in your application now to deal with all kinds of like data anomalies. This is the strength of a relational database is that it can make it a lot easier to write code, right? You can make a good application with less effort because you don't necessarily need to handle a lot of situations. When you can rely on transactions, you can rely on the fact that I can do a whole bunch of different things and they either all go in as a single atomic operation or they fail. And you can rely on the fact that when you have a connection, you're never going to see partial data. You're never going to see an inconsistent state. You will always see it consistent. I'm not going to see like somebody else was modifying data and they were 50% through, and now I might actually see data that's 50% of the way updated, but not 100%. So these are some of the strengths of working in a relational system. And what we've been doing is kind of rolling back the covers a little bit and talking about how that's done. Now, what I'm going to do now is I want to kind of go real deep and show you in kind of some practical ways some of the implications of the Postgres design. And the vehicle I'm going to use to do that is this content. Now, this is a deck that Grant McAllister put together. He's a senior principal in RDS. It's his talk, and if you ever have a chance to hear him give it, go listen to him. But it's also, I'm reusing it here because I think it's just the content of these slides is a great vehicle to go very deep on a couple of key concepts. So this presentation is about something called HOT. HOT stands for heap-only tuples, and what this is this is an optimization inside of Postgres that was introduced. It actually turns out it's a very important optimization in Postgres, especially from the perspective of performance, of having an application that performs well. So I'm going to kind of, we had a description here, but let's just kind of walk forward and I'll kind of explain what HOT is. And I think in the process of explaining this, I'm hoping that this really connects a lot of dots as far as like how things are working. So all of those concepts that we introduced, I think that this will kind of help you to really kind of see how it works kind of in practice and in motion. So, starting out, this is how most people think a database looks, right? You've got indexes, and your indexes point down to a tuple or a row inside of a block. This is kind of how you think of a database working. And if you've come from other databases, if you've worked in other databases, that might kind of reinforce this idea. But this is great. As we actually just talked about, Postgres is a little bit different. This isn't actually how Postgres looks. Because in Postgres, we have what Vinny introduced. At the top of our blocks, we have what we call those line pointers, remember? So in Postgres, and in Aurora Postgres, this is the same in both, what actually happens is your indexes point down. So we'll say we've got a tuple down here, or a row, same thing. And we'll say we have line pointer number 1. All right, well, all three of these indexes now are pointing down at line pointer number 1 at the top of the block. And now that line pointer is going to point down to the tuple. Now, what happens if I want to update this record? Now, if you're coming from a background of looking at other databases, what would happen is it would just update that record, right? It would just kind of edit this row. and then somewhere else it would make a record of that change so that it could go back and undo that if it had to, kind of roll the change back. But that's not how it works in Postgres, and we just went over this as well. In Postgres, what we actually do is, if I'm just updating, now this is a whole tuple. This has got maybe like 10 attributes on it, or 50, or 100. But it's a single row with a bunch of columns. And maybe I'm only updating a single column. Maybe I'm just flipping a bit from 0 to 1. But what Postgres has to do, just to flip that bit, is actually copy the entire tuple to a new version. So really, tuples are kind of immutable in a sense here. You could think of them that way, that in Postgres, once a tuple goes down, we don't go in and change those bits on the disk. At least not. Now, sort of once you get into the internals, there are ways, and we'll get into that. But just think about it from a high level that, like, whenever you update a tuple, what Postgres, the way it works in Postgres, and the way this database is implemented in Aurora Postgres, is that we're going to make a new version of the tuple up here. We're going to allocate a whole new line pointer, number 2. All of the indexes are now going to point to that line pointer, and that line pointer is now going to point to here. And I want to point something out real quick. Index A could be a unique index. And maybe the column that we updated maybe was not that column. But what's now happened is that inside of this index, we now have 2 entries pointing to the same, 2 entries for the same record, right? So just think about that for a moment. Even in a unique index in Postgres, you're going to have multiple entries. And then what will happen is Postgres will sort it all out. So when if I want to look up that one individual record, then what's going to happen is Postgres is going to realize, oh, there's multiple different versions of this, and it will look at those versions, and Postgres will figure out which version is the one that I need to see. Because maybe this is a report that started running 2 hours ago, and this report needs to see version 1 of the tuple, because we need to maintain that consistent view of the database. We don't want to see an uncommitted update. On the other hand, maybe I just updated the data, and that same transaction is now doing a select on the same row that he updated. It might not even be committed yet, but because I'm within the same transaction, I should see the results, right? I should see my own updates. So in that case, Postgres is smart enough to know, oh, now I need to see this uncommitted row right here because it's my own row. It's my own transaction. So Vinny also introduced page inspect. This is a nice graphical representation, but one of the really cool things about Postgres at AWS is that even as a customer, we have this really cool thing called page inspect. And even as a customer, any customer in the whole world who has an RDS Postgres instance, you can actually see the bits inside of your blocks, and you can watch this happen yourself. And there's 2 different, page inspect has sort of 2 different useful things it can do. This get raw page function you can call directly, and you can literally just pull a binary copy of your 8K block right down and look at that. You could look at that in a hex editor of your tables. You can actually see what that's doing. And then secondly, there's a SQL interface where we wrap that in a function, and it looks like this. So in SQL, I can actually decode all those little headers that we talked about in the block structure, all of the tuple headers. So what we're looking at here, we're using page inspect to look at the block header, first of all. And we see a checksum for the block. We see some other things, the size of the page. And then here, we're now looking at a record. So this is now looking at the tuple. And we see some of the things some of the columns, if you were paying attention earlier, the attributes of the tuple we talked about, like the xmin and the xmax, the lengths and things like that. And then, of course, here's looking at the index. Now, let's do the update. I'm going to real quickly and then the index, you also can see this thing called the ctid is what identifies the line pointer. And so when we go back to here, we talked about the index pointer, the line pointer, and the line pointer going to the tuple. Now coming back to page inspect, we can actually observe the same thing in our very own database. We see that there's the index entry, which says block 0, line pointer number 1. And when we looked at our records, indeed, we saw line pointer number 1, and here's the tuple that that line pointer is pointing to. So what happens when we do the update? Let's update our table. We'll update we'll just set this column last updated. Notice the first thing right off the bat is that you can see in the page header, this tells the lower and the upper parts of where the free space is. And that's changed. Just take my word for it from the last slide. More importantly, we now see our 2 tuples, just like in the graphical picture that I had a moment ago. And we see the 2 records in the index. And we can see that this index entry, our first index entry, block 0, tuple 1, is pointing to the first line pointer. And we see that we have a second entry in the index. Remember, there's only 1 row in the table. If you select count star, you're going to get 1 row. But there are 2 entries in the index, 2 tuples in the block, or on the page. So this is sort of starting, I hope, to give you kind of a visual on exactly what Postgres is doing under the covers. Now, I'm going to talk a little about what a hot update is. But first I want to just talk about how we get a hot update. So because, take my word for it, it's an optimization. It's something good. It's something you want, right? But it does, your workload matters a little bit. So let's say that we have our tuple that we're about to update. But in the meantime, you are inserting a whole bunch of data into this table, OK? So in the meantime, we've gone and we've filled up our block. Now we go to update our record. But now what do? The block's full, right? Well, what we have to do now is we still are able to do that. We can just put the v2, the updated version of the tuple, in a different block. However, unfortunately, this means we can't do a hot update too. So that's sad. Rule number 1 for hot updates is that it has to be able to put the updated version of the tuple in the same block. OK, so let's say that we make sure to reserve some space in the block and we don't run out. But we're going to update a column. We happen to update the column that index A is indexing. OK? So now we have to add, we're changing the value, and we're adding a new entry in the index with a different value. Well, that actually disqualifies you from doing a hot update as well in Postgres. So the 2 rules for getting hot updates are that you need to be able to put, if you can put the tuple in the same block, and if you're not updating any columns which are indexed, then you can get a hot update. So what's a hot update? A heap-only tuple update just looks like this. Just like before, I put my v2 of the tuple in the same block. All right? And just like before, I allocate a new line pointer number 2, and that line pointer points to my tuple. This structure makes a complete tuple. But now is where I do something different. Remember last time what we did is we went and we added the new index entries, and they pointed a line pointer too. Well, what the Postgres community came up with as a really cool optimization was, well, instead of having to update all the indexes, how about if we just chain the rows? So what we can actually do is we can put an entry down inside of this tuple that links back to line pointer number 2, which now points at the second tuple. All right, and let's say we update it again. Now we've updated the same row. So again, we're still 1 record in the table, but we've updated it twice. So now we have 3 tuples in the block. And we can do the same thing. Again, line pointer 3, and then tuple 2 points to line pointer 3. All right. Now what happens if we run a query that we want to look at this row? Well, what's going to happen is, so we're using our query, let's say, goes through index B. All right, so we want to look up the row, and I'm saying where city equals Dublin. So we go to the city index, which is, I guess I should have used C for that, but it's B. And we're going to find the entry for Dublin, which is the yellow one right there. And what we're going to do is we're going to follow that reference, and that takes us to line pointer 1. And now what Postgres then is able to do is just start following. It can just follow the chain. So it follows from v1 to line pointer 2, and it just keeps following the chain and reading the tuples inside of this same block until it finds the record that it needs. And it's able to figure out, using the same rules, the same visibility rules that it did before, which one of these should this particular session see? Which version of the row is the correct version for me to get, maintain my consistent view of the database, all of the rules that we need. Now, we can also see this with page inspect, but I'm going to, given the time, I want to kind of move quickly. I'm just going to kind of skip over some of this. But you can, just real quickly, you'll see we have a single entry in the index. That entry points there, and that guy points down to the bottom. I'm not going to kind of dig super deep. Here's with the second update. Again, single entry in the index. We have a little bit of extra information here in something called the info mask field, which is actually, it's a bunch of bits, and the bits can be set, but in this view, it's actually telling you the names of the bits, which is really convenient, so you don't have to look at a hexadecimal number and try to figure out which bits are set and what they mean. And the same thing, the index points there, and then the row points and the row points. And this is like, you could literally create a table, insert one record, update the record twice, run this SQL, and you would see this on your own database. You can actually look at the block level and see it just like this. It's fantastic. It's one of the things I love about Postgres and RDS, is that we give this level of visibility to you about your own databases. Now, we mentioned a little bit about with hot updates, there's kind of an obvious benefit that you're not having to have this extra index entries, right? But that's not the only benefit. There's actually there are a lot of reasons these hot updates are important. And the more we kind of walk through these, I think this is great. This will reinforce some of the concepts about how the internal structures work, and also at the same time you're learning about hot updates and why they're important. So a second case, and a second reason hot updates are important, is for pruning or cleaning up. Now, we talked earlier about vacuum and how vacuum is really important. So the basic concept here is that we, at a certain point in time, we know that like our oldest record, nobody is ever going to look at that anymore, because that thing, at some point in time, all the transactions who might see this old version are gone. This record has been deleted. It's obsolete. At that point in time, we can clean it. It's safe to clean up, right? So that's what vacuum normally does. Vacuum is the process of kind of cleaning up. It's kind of the normal process of cleaning up. But with hot updates, we can actually do something a little bit more efficient. We don't even need to wait for vacuum to happen. We can start doing some on-the-fly cleanup that we call pruning. And this is pretty cool. So we've determined that this tuple here is obsolete, meaning nobody is ever going to need to see that tuple again. We know the oldest transaction that's currently alive in our system. We know he's newer than version 1. So let's just delete that, right? Do a little bit of pruning, delete that record out. But now we might have a problem, right? Because now our indexes are pointing at line pointer 1, which we've lost our link. But that's actually a pretty simple thing to do. And the simple fix for that is that not only can the tuples, so I mentioned that a tuple can be chained and point back to a line pointer. Well, in order to support this ability to do on-the-fly pruning, the next really cool capability that Postgres has is that these line pointers themselves can also chain. So what we can do is we can just, when we remove the row, we just make this line pointer point directly to line pointer number 2. This enables us to remove the old tuple without having to go, without changing anything outside of the block. We can just start to do these on-the-fly cleanups of blocks. This is not vacuum doing this. This is a pruning that just happens in the system before vacuum ever gets around to running. And we can just do this on the fly. This is like an additional reason hot updates are so important. Let's say that now the clock keeps moving forward, and now we've determined that this tuple v2 can be cleaned up. It can be pruned out. So we remove that guy. We don't even have to link number 2. We can just update we can update the reference in line pointer number 1 and just make that guy point to 3. And now we've actually freed up a slot. Well, we've potentially freed up one of the line pointers. We can also see this with again with page inspect, so you could reproduce this yourself and inspect what it would look like. And what you're going to see is you look at these line pointer flags. You'll see flags saying normal, and then the info mask, you'll see the hot updated one, right? And what's going to happen is after that, now in this example here, what we've done is we have a single record and we've updated it about 35 times. So you've got all these 34 different versions of this tuple that are sitting in this table. With no vacuum, with only just the on-demand pruning that happens, what happens after the prune runs is it looks like this. Now you see the flag say line pointer unused, meaning that all these entries have been freed up. And then what we see is that there was this last entry which is still here, and we have two. So the top one points down to here, and then we have this guy pointing there, and he's pointing there. So there's 3 versions of the row that are currently left in this block. This is the first one in the chain, the second one in the chain, and the third one in the chain. The second and third are at the top of the slide. So that's a little bit about the line pointers. But stepping back for a minute, one of the things that I said you need to have for hot updates to work is you need to have space in your blocks. And I remember I showed a picture a little bit earlier about how if you fill up your block all the way, then you can't get this great optimization. So what determines how much space we get in the block? Well, that's actually something we can configure. And the default setting, as it turns out, is it's a percentage. And the default setting in Postgres is 100%, meaning this is called the fill factor. And the fill factor is something you can configure at an object level. And you can say for this object, I want you to, when you're inserting new records, put them in the same block until it is 100% full, which is the default value. And so let's take a look at this. So we set up a test to try to illustrate this. And in our test, what we did is we had these inserts running on a continual basis. And while those inserts were running, we took a single record and we updated that record 100 times. OK? Well, what happens is the inserts go and they fill the block up. And then when we update that tuple, it's going to go to another block. Now, in the meantime, these inserts keep running and they fill up the second block. So the next time we update the record, we now have this tuple going over in the third block. Now, what this means is that when I want to do a single key lookup, I go through my index, I traverse my B tree, right, to get down to my leaf node. My leaf node points me to the first block. Well, actually, I'm sorry, going back. I go to my index, I go to my B tree, I look in my B tree of my index, and I actually have 3 entries for the same record. I'm doing a single key lookup. Maybe this is on the primary key of the table, meaning guaranteed unique, but there's still 3 entries in my index pointing to 3 different blocks because there's 3 versions of that row. Now, I'm guaranteed only one of these is going to come back in my query, but I just don't yet know which one it is until I look at all 3, because the visibility information is actually in the tuple itself, not in the index. Which is also, by the way, another important side note, that in Postgres, indexes don't contain any visibility information about the tuple. So you will almost always, there is one exception to this, but much of the time, you can never look in the index and know if a tuple is visible. You generally have to go look at the tuple itself. There is one other mechanism where Postgres can get some hints and sometimes avoid checking the tuple because it can already know. But generally, it has to look at the tuple. All right, so let's say we set the fill factor to 90 instead of 100, because I want to be able to keep some of my updates. Well, with the fill factor of 90, now, when it gets to 90%, Postgres leaves 10% of the block empty, and it starts moving the inserts to the next block. So what this means is when I update my record this time, it's able to put the version 2 of the tuple in the same block. My workload keeps running. This guy gets to 90%. The next time I do an update, though, I'm still back to moving to a second block. So we're still in this situation where we go into the index, and we still have multiple blocks that we need to visit, multiple versions of the tuple. So, well, I'm not happy with that. You know what? Let's just set the fill factor to 10, right? I'm going to make sure that I always get my updates in the same block. Well, this will work. All of my updates are going to go in the same block. But the side effect of this is that suddenly my table is going to need a lot more blocks for the same amount of data. Exactly. Right? So now the table gets a lot bigger. So what does that look like in practice? A real simple way to look at that is that we set up a test where we just had inserts running at about 2,000 inserts per second, and then we updated the row 100 times. And then we just measured the number of blocks that we had to access to fetch a single record with a key going through an index. And then we looked at how long to do a table scan. You might need to do a table scan if you're looking at a column that doesn't have an index, or if you're doing an operation that just needs to look at all the rows, like if you're aggregating data, for example, to get like a sum or a running total, something like that. So there's a lot of reasons you might need to do a table. You might want to do a table scan. Well, with a fill factor of 100%, not surprisingly, as we saw, to get that one row, we have to look at 101 blocks in the table. All right? So we have every single version of the rows going in a different block. But the table scan ran with about 5,500 blocks. We could fetch the entire table. When we set the fill factor to 90, made a dramatic difference. It dropped us from 100 blocks down to 18 blocks that we had to access for this test. How much bigger does our table get? Only up to 6K. It's not terrible. How about 50%? Set the fill factor to 50, 5 blocks for that single key fetch. The table's now about double of what it was originally. And looking at our 10% fill factor, sure, only 3 blocks we had to access to fetch that key, but now we're looking at a table size that's more than 10 times the original size of the table. Now, a term that you'll hear a lot when you start talking about Postgres is you'll hear people talk about something called bloat. And I think a great point in this slide is that bloat can look like a lot of different things. Usually when people talk about bloat, they're thinking about like vacuum is not doing its job and it's not removing rows fast enough. But this is an example where it's really bloat, but it's just by configuration. Like you've just literally configured your table with a 10% fill factor and you've made your table ginormous and very inefficient from a perspective of space usage. Now there might be some situations where you want this by design, but it's just kind of a good thing to point out. There's one other really important thing in this slide, which is that in order to generate this test, I didn't highlight this at the beginning, but if you look at the top, it says we had a long-running transaction. Now, why did we have a long-running transaction? The reason we need a long-running transaction is because you remember I talked earlier about how Postgres can do that on-the-fly cleanup. Well, what the long-running transaction does is the long-running transaction guarantees that somebody needs to see the old version, so it's blocking that cleanup process and keeping all these row versions around. So what happens if we don't have a long-running transaction? Without the long-running transaction, our single key, so our table sizes are going to be the same. That's not going to change. But what happens to our single key fetch time? So with a fill factor of 100, instead of having to visit 101 blocks, 2. The on-the-fly cleanup was able to clean up everything except for 2 blocks. And then with a fill factor with all of the remaining fill factors, the on-the-fly cleanup was able to clean it up all the way down to 1 block. So the on-the-fly cleanup makes a really big difference. Another thing is you need to pay attention to long-running transactions in Postgres. Your longest running transaction is a really important thing to keep track of. So another way to illustrate this is we set up another test where we just have that update statement running. Okay, and we let that update statement run for about 60 minutes, and we do that long transaction. Just kick off the transaction and let it hang open. So we block the on-the-fly cleanup, and then we just watch the size of the table plus 1 index for 60 minutes, and we graph it out. And just doing a steady stream of updates for 60 minutes, this is what the table size does. while you have the long transaction. This is what you would expect, right? Every time you do an update, you're adding a new version of the row. And we can't do any cleanup because somebody's running a report and they need that really old version. So as long as that report's running, we need to hold off on the cleanup. So what that's going to mean is the table is going to grow for 60 minutes. Let that sink in too. This is, again, why it's important. The more you understand about kind of the Postgres architecture, you'll start to pick up on ways you can design and ways you can manage your systems to really get the most out of it. So it grows just kind of like what you'd expect. Now, what happens if we're actually getting, this is about hot updates. What if we're getting hot updates instead of regular updates, but we still have that long transaction? Well, the line looks like this. The difference here is mainly in the index size, because with the hot updates, we don't need to have extra entries in the index, but we still have to have all those versions in the table. So the table is still growing at the same rate. Can't do any cleanup. But what if instead of having that one really long transaction, we just have 1-minute transactions? Well, we're running the test for 60 minutes. We're just holding transactions for a minute. Let's see what happens there. Well, that on-the-fly cleanup is able to make a little bit of an impact, but not a huge impact. So you see that with that 1-minute transaction regular, it's a little bit lower of a curve, but the table is still growing quite a bit. We're going to need a vacuum process to come through and clean up a lot of that space later. And the hot updates, there's also a slight improvement, but not huge. But what happens if we don't have any open transaction at all? With no open transaction at all, the same test, this is what we get. That's our table growth curve with no open transactions. And what if we're getting hot updates? With hot updates, the line looks like that. With hot updates happening and no open transactions, the table growth is completely contained with a steady stream of updates. If we just zoom in on the index itself, this was the index growth with the long transaction. Now, this was, like I said before, with the hot updates, the index doesn't grow very much. So you see, even with the long transaction, hot updates kind of contains our index growth pretty well. With the 1-minute transactions, here's how much better the index growth is. But literally all the rest of our test cases that we ran, the index doesn't grow at all. So when you get rid of that long-running transaction, when you're using hot updates, again, it really helps contain, this is another form of what we call bloat, but it helps contain this sort of like growth of your objects and growth of your data. So I'm going to skip over a couple of slides here because I want to make sure to get to kind of one more important section at the end before we run out of time. So jumping forward, something that people wonder a lot of times is the impact of indexes. What kind of an impact indexes have in thinking about indexes. And what I'm going to do real quickly to kind of wrap this up is I'm going to take and look at I'm going to look at sort of some simple benchmarks where I slowly add more and more indexes to a table and see what the impact is. And I'm going to look at that in combination with hot updates. But before I get into that, and in order to kind of understand where we're going to go next, I need to sort of dive into one more kind of important concept, and this is called full page writes. So Postgres has a thing called full page writes. And this is great because now we're going to kind of back up a little bit and back to our sort of foundational concept. We've talked a lot about block structures. Now I'm going to step back and talk about the write-ahead log. Now Vinny introduced it. He made the comparison to a file system journal, which is a good comparison. And the basic idea, it's also, or a redo log, is something that's called in other databases. The basic idea is that whenever you change something, first you put it in the log and then you make the change, is kind of the basic idea. That's the idea of write ahead. And also, well, so we'll start there. Secondly, you can make changes in memory. Well, here, let's just walk through what it looks like. So let's say we update a record. When we update a record, the first thing we do is we update a record, we update a block in memory, but what do we have to do when we update that block? Well, what we have to do is we have to take our update, and we also have to write that update into the wall stream. So we call this a stream because, as we were saying earlier, it's append only. It's just you're always appending to the end of it, and it's always just being written down to the disk. So what we're going to do is we're going to put that block, that change, into the stream. But there's one more thing we're going to do, is that the first time that we touch this block in memory, we're also going to put a copy of the entire 8K block into the wall stream. That's a lot of bytes that we're putting into the wall stream, if you think about it. But why do we do that? Now, if we update the same record a second time, okay, we still put our change into the wall stream, but we don't need to put the full block into the wall stream again. All right? Now, why do we need to do this? The reason that we need to do this kind of comes back to the second process that we talked about, which was this idea of checkpoint. And really what this comes down to is that we have sort of these two parallel data structures that we're managing. One is the wall stream, or the write-ahead log. And this is kind of just a log of all of our changes. But secondly, we have the actual files themselves, our data files. Like this is the file that has my table, and it has my heaps, and it has my tuples. And this is actually like the source of truth. This is my real data. But the thing is that in Postgres, what you don't want to be doing is every single time you change a page in memory, you don't want to have to flush that block out to the disk. You want to be able to batch it up, make a whole bunch of updates to the block, and then at some point in time, push that image down to the disk, and then make a whole bunch more updates to the same block, and then eventually put a fresh copy on the disk. But you don't want every single time you're touching a block to write the entire block out to the disk. That would be very inefficient. It's far more efficient to use it like a cache. That's called checkpoint. That's what that process, the checkpoint process is the process where we kind of slowly work our way through memory. We take that block, and we've made a whole bunch of updates, and we finally flush all of those updates down to the disk. So what the wall stream is for is, now let's suppose that we've updated this block about 30 times, and then we crash the system, but we haven't written the block out to the disk. Now what just happened? Did I just lose data? Well, I didn't. And the reason that I didn't is because the block never got written to the disk, but the wall stream did. So what will happen is Postgres does crash recovery. And what crash recovery is, it'll read the block back from the disk, and it says, oh, this block was updated at 3 o'clock, so I'm going to replay all of the changes that happened after 3 o'clock, and I'll just update the block again. And now, by reading the wall stream starting at 3 o'clock, because that's when the checkpoint was, so the checkpoint tells me what time did this block hit the disk last. It tells me this block is current as of 3 o'clock. That's my checkpoint was at 3 o'clock. So I know when I do recovery, when I do crash recovery, I start replaying my wall stream at 3 o'clock. That's when my last checkpoint was. And then I just replay all the changes that I made. And now I can reconstruct the exact state of that block as it was in memory at the time of the crash. And I haven't lost any data. So this is what allows us sort of the efficient process of making a whole bunch of changes in memory without needing to flush the block to disk every single time. All right. And then there's kind of one other piece in here too, which is that wall data, we also want to keep that around for like long term as well, so we do archive that data off. But there's kind of one little nuance to this. And the nuance is that in Postgres, our blocks are 8 kilobytes. Now that's configurable, but in RDS land, it's always 8K. And actually in many databases, that's kind of a default. But operating systems do not operate in terms of 8 kilobytes. So when the checkpoint process wants to write 8 kilobytes of data down to the disk, it doesn't do an atomic 8K write. In fact, most operating systems, certainly Linux, generally operate with a 4 kilobyte page size. So the operating system, when I say flush that block down to disk, the operating system translates that into 2 I/O operations that are 4K each. And what if I'm doing my checkpoint and one of those I/Os gets to disk, and then right at that moment the system crashes? Now I have a new problem. I have a problem where previously at least I knew I could start it at 3 o'clock and I could replay my changes, right? But now I have a new problem. I have a block we call it a torn write. Basically, I have an inconsistent or a corrupted block because half of it's the new version, half of it's the old version. I can't start at 3 o'clock and start replaying data on top of that. Well, this is the reason that Postgres does the full blocks into the wall stream. The first time, what Postgres does is that in the case that the checkpoint was not complete, it goes back to the previous checkpoint and starts replaying data. Now, it doesn't have a block image from the previous checkpoint. This is the only block that we've got. But luckily, when we start replaying the wall stream, the first time we touch this block, we stuck a copy in the wall stream. So what we have is that so at 3 o'clock, there was a failed checkpoint. But at 1 o'clock was our previous checkpoint. So at 1 o'clock, I start replaying my wall stream at 1 o'clock. And at 2 o'clock, I have this full block in the wall stream. So I can now take that full block and copy the entire block down to the checkpoint, or back to the data file, and then continue replaying my data. So the full page writes are a very important mechanism in Postgres to prevent a torn write, meaning kind of a half-completed write by the operating system from corrupting data in our database. And this isn't unique to Postgres, actually. For example, Oracle does exactly the same strategy when you put it. If you ever did sort of the old-style hot backups, where you used an OS utility to back up your files by just copying the files, you'd put your Oracle database into hot backup mode, and Oracle started putting full block images into the log stream. Exactly the same strategy. This isn't unique to Postgres as a general strategy. But there are some important implications of this. In Postgres, first of all, this is always happening. In RDS Postgres, this is something that's always turned on and it's always happening. And what it means is that the first time you touch a block after a checkpoint, there is a significant extra expense in terms of I/O. So let's just kind of, in the context of an index, look at what this might mean. If we have a right-leaning index, like a sequence number or a last updated time, something like that, then what's going to happen is we're going to insert a new record into the table. Say we insert record with a value of 201. We hit the root tree, we follow that all the way down, and we've touched about 4 blocks. Now we do the next record, the value of 202. Well, this time, it hits the same 4 blocks, right? So we don't add any new blocks. With a right-leaning index like this, what you can see is you'll probably get maybe like 1 full page write on this leaf node, but that's about it. But now, what if we have a different index? What if we have like a GUID or something like that, where it's completely randomized? All right, let's look at what that might look like. Well, the first time we insert number 124, and we hit those 4 blocks. Now our next insert is a number 99. In order to insert this record, we go down the other side of the B tree, and we have 3 more blocks that we've now added. And then our next record is 161, which adds another 2 blocks. And every time you're touching more blocks inside of the index, you're increasing your odds that you're going to be doing full page writes. So what you end up with is the more blocks you have to touch in the index, the more I/O that you have to do as you're updating your system. Now, I'm going to bring this full circle, and remember hot updates. One of the benefits of hot updates was that when you did the heap-only tuple, you didn't update any of the indexes, right? Because we just made the change in the data block, but there was no updates to the indexes. So what that means is that this sort of write amplification effect is directly observable on in terms of I/O amplification in the wall stream with hot updates as well. So when we do a hot update, and then I dump the wall stream of what just happened, what I see is a single full page write, and that's for the table that I just updated. But if I don't get a hot update, meaning that I now have to update indexes, for the exact same update, this is what a dump of our wall stream looks like. Now I have my same data page update from the table, but in addition, I had 4 full page writes going out to the index. So this is kind of one of the reasons that hot ups are important. It's not just about that one little record in the index. It's about, that's triggering entire blocks being written out to your wall stream. So what that turns into is 3 kilobytes with the hot updates of I/O that I had to do, 16 kilobytes, 4 times as much I/O when I didn't get hot updates. Another way to kind of visualize this same thing is looking at like kind of taking 100 clients and spinning them up and running a benchmark like this. You'll see that that write I/O difference translates directly into the TPS I'm able to drive on this kind of simple benchmark, where starting off, if there's just 2 indexes, okay, it's not hugely different, but you see that the hot updates are able to drive some more transactions through. But as you go down the line, it gets worse and worse and worse, to the point where once we have 64 indexes on this table, there's a 35x difference between how many TPS I can drive with hot updates versus without the hot updates. And it's not just updates. One last thing to look at, I think, is vacuuming as well. We talked a bit about vacuuming earlier, and the vacuuming still has to run. It has to clean up some of the data in the blocks. Vacuum is a serial process, and one of the important things that vacuuming has to do is, in order to clean up the data block, the first thing it has to do is make sure that there's no indexes referencing that line pointer before it can get rid of the line pointer. All right? So what vacuum will do is, first it gets a list of line pointers which are candidates for removal. And then it has to go scan all the indexes. And there's no reverse pointer that goes from the line pointer back into the index. So the only way to make sure that my line pointer is clear and it's safe to remove that guy is I have to just literally full scan, like read the entire index beginning to end and make sure there's no references to that line pointer. And that's a serial operation. So the bigger your indexes get, the more expensive that becomes. So what does that look like? If I'm doing hot updates, same kind of test where I sort of slowly ramp up the number of indexes. Well, I did 1 million updates of a table, and I made sure they were all hot updates. How long did it take me to vacuum that table after 1 million updates? Well, with only 2 indexes, the vacuum, you see it took less than a second. We get up to 64 indexes, and it takes a bit longer, but you still see we're still like at 6 seconds. We're still well under 10 seconds with 64 indexes. What does that look like if I don't have hot updates? Now, without hot updates, remember I have to add all the extra entries into the index, right? Here's what it looks like when we add in the not hot updates. Now, I've left the red on the chart if you can still see it. Because now we're talking about literally a 100x difference between the hot updates and the non-hot updates and how long it takes me to vacuum my index in the case with 64 indexes out there. Just to kind of bring this home, I'll kind of walk through one real quick practical example, and then we'll wrap this up. This is sort of a case that's really common. And the case is, like, what if I have a table, but if I want to keep track of the changes to my table, because I have like an external system that I want to keep in sync. So one strategy that people use to do this sometimes is they take their table and they add a column called last updated, right? And whenever you update a record, you update the last updated time. So when I want to go synchronize my outside system, so let's say I'm going to build an outside system and call it that's not. So this was a mistake. It says data warehouse, but nobody calls them that anymore, right? We call them, data lakes now. So we'll fix that. Anytime that what we do is whenever we want to update our data lake, we know, well, the last time I updated the data lake was yesterday at 3 o'clock. So I'm just going to search for all the records where last updated is after 3 o'clock yesterday, and I'll copy those records to my data lake, right? So that's a simple strategy. But over time, the table starts to grow, and this is doing a full table scan on that last updated column, right? So people start to complain, it's taken too long to run this update job. So what does somebody do? Oh, and I should point out, the red columns are the columns with indexes, all right? So what somebody does is, well, they add an index on the last updated column. So we'll change that to red. So now great, everything goes fast again, right? So now I can get my updates to my data lake. My update job starts going really fast because now I'm getting, of course, an index scan instead of having to do a full table scan to get my changes, my change data, and to synchronize my data lake. OK, so that all sounds great. But there's a big catch. We've been talking for almost an hour now about hot updates and all of the impact and how important it is to get hot updates in your database. Well, before we made this change, before somebody went in and just added this little index, anytime that we made updates to columns 1, 3, and 5, or the last updated column, we were getting hot updates, right? Because as long as you can fit it in the same row, and as long as you're not updating one of your index columns, you can get a hot update. And you get all the benefits that come along with that. But think about what we just did. We added the last updated column. There's a trigger on this table, right? Every time you touch anything in the table, you have to update last updated. So every update updates last updated. We put an index on last updated. Now, no hot updates. We're done. It's out. So every time we update anything in this table, it has to be a regular update because we're always updating an indexed column. This is sad. So it's actually a little scary too, and just one of those things to sort of look out for. You realize that like even a little thing like adding an index can have sort of these secondary effects that you might not anticipate if you're not paying attention. There is actually a much better way to do this, by the way, because you might be wondering, well, then what am I supposed to do to keep my data lake up to date? Well, in Postgres, remember we have that write-ahead log. And Postgres, for the record, does have like fantastic capabilities where you can essentially get direct access to that change stream, where Postgres can set up an auxiliary process that just reads the write-ahead log, decodes the data there into a change stream that you can plug directly into DMS, or you can plug directly into a number of third-party external services, and this is called logical decoding or logical replication. These are built off of the wall stream, which this is the happy path. This is the way that you want to be doing this sort of a use case, where you're trying to keep an external system in sync. So that's a fantastic deck, and I hope that the hot update stuff is interesting, but I think the best thing about this deck is that it's a way to really illustrate the stuff that we talked about in the first half when we kind of gave some. Now, this only went deep on kind of the block structure and the wall stream. There's about 100 more things that we want to go into. I'm just going to real quickly, as I kind of wrap up, point out sort of one sort of final thing, which is that, this is the wiki page. We're updating this. We're updating this wiki page. It's been updated a lot since we first put the page up. So I would encourage you guys to go back here and take a look at this wiki page. In particular, so when we come back at 3 o'clock, as you're sitting down today, working on your system, if you see a ticket, if you're working on writing some code and a question comes to mind, you can either throw it in the chime room or you can jot down a piece of paper, bring it back at 3 o'clock. At 3 o'clock Dublin time, I believe that's 4 o'clock UTC, right? I think that's an hour later. 2. All right, thank you. 2 o'clock UTC. We'll have more of kind of a discussion-oriented thing to be able to kind of go wherever you guys want to go. And then I'll also have a set of hands-on labs. I really think getting your hands onto Postgres is a fantastic way to really kind of solidify this stuff in your memory, right? I'll introduce our contest that we're doing for the week. And one last thing on this wiki page, there's a whole section at the bottom called useful links. And this has sort of the cream of the crop, a handful of, I think, some of the most important. There's a lot of like other links we could put here, but I've tried to just keep this to kind of like the critical sources of information that you find. So to learn more and to keep going, like we've just scratched the tip of the iceberg here, but there's a lot of really good resources. Sort of in particular, I would point out, like today we talked a bit about architecture and theory. I have a whole section here. So Andy Pavlo from Carnegie Mellon, his entire advanced database systems class, he posts all of his lectures this spring are recorded and posted on YouTube. All of his class materials as PDFs, the homework assignments, everything. Like that's a great study on your own resource. There's a couple other places as well. Hironobu Suzuki, who in fact works here, I believe, right? Yes, he does. His online book is, I think it's very good. It's kind of like concise. It's not as long as some of these other things, but he has some great illustrations. And it's just sort of a great, I feel like, introduction to architecture. It makes the illustrations in particular, things like transaction ID wrap around and how the transaction clock works and some logical replication stuff. It's just a great on-ramp to getting a hold of the architecture well. So yeah, I would particularly say to follow up and to get more architecture stuff, these 4 links are some good resources that you can do. So we'll probably touch on some of the stuff more during the week. And that's a wrap for today.